In this video, we're going to go through absolute entropy and entropy change. So we're going to begin by talking about entropy and enthalpy. Enthalpy is a term that you're familiar with. Enthalpy we represent with delta H, and that's just the heat content for the system. We know that if we have a negative delta H value, it's exothermic. If it's a positive delta H value, that's endothermic, meaning it's absorbing heat. Now, entropy is something that you may or may not be familiar with. Entropy just refers to the disorder of the system. If we have a positive delta S value, that means we have more disorder, which is favorable and spontaneous. If we have a negative delta S value, that means less disorder, which is unfavorable and not spontaneous. All right, so the second law of thermodynamics states the universe is constantly in increasing disorder. Ooh, gave you the answer already. We haven't even done this one. Okay. So our first example says, for each of the following pairs, choose the substance with the higher entropy at a given temperature, and then explain your reasoning. All right. For the first one, we have CO2 as a gas, and then CO2 as a solid. And it's asking again, which one has a higher entropy? So for A, it's going to be in the gaseous state. So when we have things that are gases, that means the particles are going to be spread further apart. Okay, so there isn't really any order to that. They're all kind of spread apart and they're moving around. Whereas when they're a solid, the particles are really close together, everything's arranged nice and neat. So we have more disorder here than when we're in a solid. Second one, we have helium as a gas at 2 atmospheres, and then helium also as a gas, but at 0.02 atmospheres. So here we're going to go with the helium where we have less pressure. So when we have less pressure, it's going to cause everything to spread out. So that would be representative of the first one, and then when everything is, when everything is at a lower pressure, things are going to spread out a lot further. So we'll have more disorder, more entropy when things are spread out. All right, in our third example, we have two things. We have calcium carbonate, and then we have calcium oxide and carbon dioxide. Now, the only one that's a gas is our carbon dioxide. Actually, these two are kind of coupled together. So the second choice here, that's calcium oxide, or calcium monoxide, and we have CO2, carbon dioxide. Those are coupled together. So the carbon dioxide, because it has a gas, is going to have more disorder. All right, so for a spontaneous process, we are going to use the formula delta S for the universe is equal to delta S for the system plus delta S for the surroundings, and we want it to be greater than 0. At equilibrium, we want it to be equal to 0. Now, delta S for the system is the same as delta S for the reaction, and we're going to find that using this equation right here, which is the sum of the delta S values for the products minus the sum of the delta S values for the reactants. All of the values for the standard entropies can be found in the back of your textbook. Okay, so this is going to look very similar to what we're doing with enthalpy. So let's look at our first example. It says, use thermodynamic data to calculate delta S for the following reaction. All right, so we're going to need to go and look up all of these values. Okay, so we have, let's see, NH3. If we go and look up this value, NH3 is 192.8. Oxygen, O2, is 205.2. And O2 is 240.1. and then H2O is 188.8. So we want to do the sum of the products minus the sum of the reactants. So to work this out, we are going to do delta S of the reaction is going to be equal to, we have 4 moles of NO2, so it's going to be 4 moles times our value of 240.1 plus we have 6 moles of H2O, and each H2O is 188.8. And we're going to subtract the sum of our reactants. So we had 4 moles of NH3, and NH3 was 192.8. And then O2, we had 7 moles, and each O2 is 205.3. So if we put this in our calculator and we're careful, you should get an answer of negative 114.4 joules over moles times Kelvin. All right, let's do another example. Number 3 says, use the following thermodynamic data, calculate the delta S of the following reaction. Okay, so same thing. This time we don't actually have chemical compounds, we've just got letters. Exactly the same thing. So A2B2 is 109.6. C2A4 is 121. C2 is 191.6. And then A2B is 191.6. So delta S of the reaction is going to be equal to, remember, it's products minus reactants. So C2 is just 191.6. And then we have 4 moles of A2B, so that's 191.6. And then we're going to subtract our reactants. So we have 2 moles of A2B2, which is 109.6. And then we have 1 C2A4, which is 121. And then when we put this in our calculator, you should get 603.7 joules over Kelvin. Ha, look, JK. It's like just kidding. And that's it. That's really all there is to this section.